can do it.
But then all you're proving is P is a subset of P. You're not proving P is equal to.
But if I can show this for every randomized algorithm?
But there could be some other randomized algorithm.
I'm showing it for every randomized algorithm.
Oh,
I'm saying take an arbitrary randomized algorithm. I don't know what it's doing, but I know it's using random bits. I'm going to give it random bits produced deterministically. This would get you to what's called pseudorandomness. When you use randomness on a machine, you're actually not using true randomness. You're using pseudorandomness created from some deterministic seed and then gone through some complicated process. And then this whole study of how to remove randomness is about this. Okay? That's what you have to show for this case here. For example, you might say, so then another complexity class that comes up is you could say, well, I know P is efficient in terms of time. What about efficiency in terms of space? This is a class that's called P space. It's a class of all problems solvable in polynomial space. And now you can ask, well, what is the relationship between P and P space? This is a very important question because it's asking, when can I trade off space for time? If you ever written code where you cache the results of a computation to use later, you're saying that I'm going to trade off time to compute this result for space in storing this result. Every time you do dynamic programming, you're saying that by memoization, I'm going to trade off time and space. So you're doing this all the time in your work. And so the natural question to ask is, under what conditions is this always possible? When can I take something that runs in polynomial space and make it run in polynomial time? Now it's not completely obvious, but it can be shown that P is contained in P space. That this statement is easily shown to be true. Why is that? Because if you're taking polynomial time, at every time step, you can at most use one bit of space, and you might reuse it. But in polynomial time, you don't have time to write down more than polynomially many words of information. So therefore, any polynomial time algorithm must run in polynomial space. But the converse is not obviously true. If I have an algorithm that uses polynomial space, I'm not telling you how much time it could take. And here's a trivial argument to say that it might be very big, because imagine that I have a counter. My algorithm is a counter that's going to count over a word of length, n squared. If the word has n squared bits, the number of times I can create a count over it is 2 to the n squared. Because that's the number of different states you can have, right? So in principle, all I can say is that P space is contained in what is called x, which is exponential time. I can't say much else. And in fact, whether P is contained in P space or not is another big open question. We don't know. Yeah.
I have a question. Is log, if I do log of n, is it still polynomial or is it different?
Log of n is better than polynomial.
Is it covered in polynomial?
Running time?
Yes.
Sure. It's at most a polynomial. Log of n is less than n.
So if I have n log n, then I would be.
That's less than n squared. It's less than n squared.
Okay.
Yeah. So formally, if you want to define this formally, P is the class of all problems that run in time n to the k for some k, union from k going from 0 to infinity. For all bounded k, not all bounded k. On a Turing machine. And one of the reasons we like to think about polynomial time is not just because it's convenient. It's because if you change your machine model, if you go from a multi-core processor to a single-core processor to a Turing machine with 2 tapes, or a Turing machine with 4 tapes, one of which is read-only, it doesn't matter. Whatever's polynomial before will stay polynomial time now. The actual running time might change. It might go from n to n squared or n to n log n or whatever, but the fact that it's polynomial stays the same. So in some sense, being polynomial time appears to be, and I'm saying this with caution, invariant over what machine you use. So it's something that's quite intrinsic. This is not completely true. If you think of quantum computers, we're not quite sure what's happening there. But it seems like this is intrinsically the case, which is why we like talking about polynomial time. Okay, so that's all the backdrop to what we really want to talk about today, which is P and this class called NP. And so like all these complexity classes represent a certain philosophical question, right? Is space more important than time? Is randomness useful or not? The question that comes up when you think about P and NP is the question of verification. Now, some of you may have heard of NP. Some of you may think that NP means not P. You would be incorrect. Some of you may have heard that NP means non-deterministic P, but have no idea what that means. That's fine, because that's not how we think about NP nowadays. It used to be, that's how it was defined, but that's not how we think about it. The way to think about NP is that it's the class of all problems. Not solved efficiently, but verified. And what does this mean? This means that for a problem to be an NP, it is enough that if I give you the answer to the problem, you can check it efficiently. I don't have to tell you where the answer came from. I can just tell you, here's the answer. And all you have to do is check to see that the answer is correct. So for example, suppose, let's use an easy example. Actually, that's not. So, at least one variant of Sudoku, and I'm hoping you all know what Sudoku is, this game 9 by 9. Let's say it's an n by n Sudoku grid. Can be shown to be a hard problem. Okay? But you can show that it's an NP, which means that if I gave you a Sudoku solution, you should be able to check that it's correct in problem time. And hopefully you can believe that. If I give you an n by n Sudoku, right, with appropriate rules about rows and columns and groups, subgroups of size or whatever, I'm claiming that you can check in polynomial time whether this is in fact the correct solution to the problem. And hopefully you can mentally say, okay, I'll check the rows, check the columns, check the groups, and it should be correct. This is an example of a problem in NP. That I give you the solution, you can check it easily. Now, of course, one way to check that the solution is correct is to produce the solution yourself and then check it. Right? If I can compute the solution efficiently, for sure I can verify it efficiently. Which basically means that I just proved that. Because any problem in P is a problem for which you can compute the solution efficiently. And if I can compute it, I can surely verify it. So this is true. Burning literally $1 million question of the day is, are they equal or not? Is it as easy to check a solution as it is to find it? Are professors important or not? That's another way to do this. And this question, apart from the issue of verification and versus computation, is very important because it turns out, and this is somewhat happened by accident in some sense, that many of the interesting problems we want to solve have the property that it's easy to check that the solution is correct, but it seems really hard to find. And since 1971, where people found the first such problem of this kind, there have been many, many thousands and thousands and thousands that people have discovered. They seem to be much more common than not. That the solution is easy to check, but it's very hard to actually compute a solution. And so, of course, what we'd like to do is prove this. Is to say, no, in fact, if I wanted to compute a Sudoku answer, it is hard to do this. You cannot do this in polynomial time. Which would be an answer to this question, in some sense. Or at least kind of an answer to this question. But we don't know how to do it. We have no clue how to do this because the machine models we're working with are just Turing machines. And it's very hard to reason with. So in this realm, in the realm of these classes, we have to reason by proxy. We don't actually reason directly. We reason by saying, well, there's this one problem that seems hard, and if I could solve this other problem, I could solve this, so this must be hard as well. And then so on, and so on, and so on, and so on. You get a whole chain of reasoning. Saying that because something was hard to begin with, this problem is going to be hard as well. This technique is called a reduction. It's normally worked the other way around, right? If I want to solve some hard problem, I reduce to some easy problem, solve that, and I reduce it. This is doing it the other way around. It's saying, I know this problem is hard. If I could solve this, I could solve this hard problem, but I know this is hard, so this must be hard as well.
But it could be another way to solve this answer, right?
No. Again, I'll be more precise in a second, but remember what I'm saying. I have two problems, A and B. I know for sure that A is hard in some sense. You know, I don't know if B is hard. I'm going to construct a reduction from A to B. That means that I'm going to use B to solve A. I'm going to use B as a subroutine in a solution for A. But I just told you that A was hard. The only way this is going to work, there's a contradiction here, unless B is also actually hard. Again, I'm going to write this all down. This is the height of it. Yes?
How do you prove that the original problem is hard?
It's turtle. It's all the way down. That's the you're just okay with it. So it's hard. It's actually very difficult. That's why this was a big result in the first half. And we'll talk about that. Okay, this is all the overview. So what we're going to talk about today is this notion of NP, of P, of something called NP completeness, of hard problems, and a very different way to think about the limits on what we can do. Last lecture was a very concrete example of limits on what we can do, made by careful reasoning. This is an argument again on limits of what we can do, but by supposition, by sort of appeal to authority, or by appeal to the past, like, these 10,000 people have tried to solve this problem, they haven't, so we can't. So there's nothing absolute in what I'm saying from now on. There's nothing that says that you cannot do this. It's just that we have no idea how to do this, and this seems unlikely. But that's it. I could be wrong. One day we could prove that he's good at it. We don't know. Okay? All right. So let's do some so we said P is a set of problems that can be computed efficiently, which means polynomial time. NP is a set of problems that can be verified efficiently. That means if someone gave me the answer, you could solve it in polynomial time. There's a related class which is called co-NP, which is kind of interesting, which is problems for which the absence of a solution can be verified efficiently. So this is weird, right? Because in NP we're saying, going back to the Sudoku example, I'm just going to give you the example and you can check and see if it works. A problem is in co-NP if you can show the absence of a solution efficiently. In other words, if I were able to give you some simple way of saying there is no solution for the Sudoku at all, it's inconsistent. For any possible Sudoku, I can tell you whether it's inconsistent or not. And that seems a bit harder because I'd have to, it seems like I have to try all possible solutions, show you that all doesn't work. So it's not obvious that just because you can show the solution does exist, that you can also show the solution does not exist. That's much harder. And that's why this class is a different class, and it's also not known whether NP is equal to co-NP or not. Where the ability to prove the solution does exist also implies the ability to prove the solution does not exist efficiently. You had a question?
NP complete is the same as co-NP, or
sorry?
NP complete?
No, it's different. Yeah, co-NP is it comes from recursion theory. Co is like complement essentially. So it's like, think of it like an effective complement. Okay, all right. So let's move on. So from now on, we're going to talk about, we're going to talk about the class P and NP. Okay? And we're going to talk about, so we have some picture that looks like this. So let me actually go back to the previous page. So I can draw a picture. So our picture might look similar. So we know that, let's see. So we know that P is here. We know that P is contained in NP, but we don't know how big it is. We also know P is contained in co-NP, because if you can compute the answer, you know for sure it exists or doesn't exist. But we don't know how these two classes interact. There's all these dots. It's kind of a mental model. This P is contained in NP intersection co-NP, but it's not actually. We don't know if it's even equal to NP intersection co-NP. There's a lot of things we don't know. It's very sad. So let's think about P and NP now. What we'd like to be able to say is the following. So we think of NP as a class of difficult problems. But we also know that P is contained in NP. So saying that problems in NP doesn't imply that it's difficult to solve. It just means it's easy to verify that the solution exists. What we'd like to capture is the idea of the really hard problems in NP, the ones that make it really difficult. So if you think of P is here again, if you think of this large class NP, and you think of P is here, right? What you're looking for is problems that are somewhere here, that are really, really hard. Okay. So we want to define notion of the hard core of NP, the things that are really tough to do. And the way we're going to define it is the following. So let's think of a problem. Let's call it pi. And we'll say that pi is NP hard. So it's hard for NP if so we'll call the problem pi NP hard if showing that this problem can be solved efficiently pulls all of NP into efficiently. Right, so this is clearly one of the hardest problems, but if I can solve this, I can solve everything. That's the idea. Does that definition make sense? I haven't shown you such a problem exists, but let me just argue, let me just answer the question.
So basically you're saying that if a particular problem can be solved in polynomial time, then that means that all NP problems are equal to P problems.
Are solvable in polynomial time.
Yeah.
Yes. So this one problem is like the test, this one problem is like the brick that collapses the house. If you can pull this out, everything falls. Was that a question somewhere? Yeah.
But you just said you can't equate one NP hard problem to other NP hard problem. You can only equate them in functions of hard problem A, problem B. If I reduce this problem, it goes to problem B. Then you have to also prove that all NP hard problems can be reduced to one problem.
So you're worried about how to prove that a particular problem is NP hard? Is that what you're asking? How do I even go about showing this?
How do you go about showing if one problem is reduction of all the other NP hard problems?
We'll get to that. There's some other hand up somewhere? No, right. No, okay. Once you have the notion of NP hardness, you have a notion, and these names are kind of annoying, but we have to be good to remember them because that's what. So notice that in my definition of NP hardness, I didn't tell you how hard the problem actually is. It could be extremely hard. For example, the halting problem is NP hard. If I can solve the halting problem all the time, I can pretty much do everything. But that's not so interesting. We're looking for problems inside NP. So if you have this extra constraint that, no, your problem should be reasonably easy to solve as well, right? Then you get the notion of completeness. So it's NP hard, it pulls all of NP along with it, but it's also a member of the family to begin with. It's not so unusually hard. Okay. All right. So now we have two definitions. Or we have a definition that. Yes.
You said pi is NP complete
if two conditions. If pi is NP hard and pi belongs to NP. So think of this as a good news, bad news situation. Oh my god, it's NP hard, it's awesome. It's horribly difficult. Oh wait, but it's in NP, it's not so bad.
Isn't it contradicting when you're saying
My phone doesn't know. So why? Just look at the definition. Don't sort of just forget everything you think you know what NP is. Look at the definition. What in the definition of NP hardness contradicts the second step?
because we're saying NP hard, we're trying to say.
Look at the definition. What does the definition say? A problem is NP hard if the problem being easy to solve makes everything in NP easy to solve, right? That does not say anything about where the problem actually lies. It's just saying that problem pulls all of NP with it. There's no contradiction. Yes.
So this is implying that there's a set of problems that are neither P or NP?
Pardon me?
So does this imply that there are a set of problems that are neither P or NP?
Ah, good question. There's a famous result from many years ago that says the following. If P is not equal to NP, then there exists some problem called A belonging to NP minus P. It is very tricky to show this. It took a lot of work, but yes, you can show this. So if they're actually separate from each other, there's something in the middle. Yeah.
Why is it difficult to show these kind of problems in NP and not in P?
Because the not in P part is hard to show. How do I show that problem is not in P?
Right.
That's the big issue here. We don't know how to do that. We are very bad at showing that you cannot do something. We're very good at showing that you can do something. Just nice. Okay, yes.
Okay, I'm still lost. So if pi, so we know that, we do or do not know that P is in it.
We know that the class, P, the class of problems that are efficiently solvable, is contained in the class of problems that are efficiently verifiable.
Like fully contained in NP?
Yes. Not strictly, just contained. Yeah.
So then wouldn't all NP hard be NP complete if NP hard defines that you're NP?
No. Think of the NPR problem as a trigger. If that trigger fires, all of NP goes to P. But that problem itself doesn't have to be in NP. So the example I gave was a halting problem. If the halting problem can be solved in polynomial time, then everything can be solved in polynomial time. But the halting problem is not in NP. I cannot verify that a problem cannot halt. I mean, I don't know how to do it. The problem with NPR could be very, very hard. Saying this NP complete just brings it down to the level of NP. So there's nothing in the definition that precludes pi from being extremely hard. That's what I'm trying to say. That's why you get this extra condition that says, no, let's think of an interesting problem that's actually solvable, or at least verifiable. If you don't like this, I would sort of let it sit in your head for a while, and for now just pretend they're the same thing. Just think about this definition, since you all seem to think this is a more reasonable definition to say that there should be an NP in the first place. But if you think about it, you will realize that you don't have to be in NP to be NP hard. Because NP hardness is kind of like a lower bound of your complexity. Saying that you're really, really hard. But you could be arbitrarily hard. Saying that NP complete says, no, you're not that hard. You're in NP. Alright. So, if I have a problem that's NP complete, then I have some reason to believe that it's going to be difficult to solve this in polynomial time. Because solving that problem in polynomial time will carry all of NP with it, right? By definition. And if I can solve this in polynomial time, it carries all of NP with it. All problems in NP are solved in polynomial time. So if I want to show that a particular problem I'm looking at is kind of hard to solve, this is a way to do it. So let's just think of how this is going to work. So I have some problem. Let's call it P. And I want to know someone has given me a homework assignment. It's like, go give me an efficient algorithm. And I want to come and say, no, I can't do it because it's too hard. What is my recourse? What kind of formal recourse do I have? What I can do is say, find an NP complete problem. Let's call it A. And then show that if I can solve P, I can solve. So suppose I can show this second statement here. Then I feel very happy with myself. Because now I'm going to go back to the person who gave me problem P to solve and say, look, if I could solve what you asked me to do, I would solve A. A is NP complete. So I'd be solving a whole lot of other problems at the same time. You need to pay me more. Or something. Because I've done much more work for you than you asked me to. Or conversely, all these other people try to solve these other problems, and you're saying that I can solve them just by doing this? No way. So I now have evidence that this problem is hard to solve. In particular, I have now shown that well, actually it's not quite true. What I've shown is that so do you see what? If I can take a known NP-complete problem and show that solving my problem would solve that problem, then I've shown that my problem is NP-hard. Do you see why? I mean, you can prove this. How do I prove that my problem is NP-hard? I have to show that every single problem in NP can be solved if I can solve my problem, right? Okay. So let's take an arbitrary problem. So I have to show this for every problem in NP. So let's take any problem in NP. So let's say, so proof. Consider any x belonging to NP. Okay? I'm going to solve x now in polynomial time. How do I solve x? Well, given A, so I can solve P. So solving P implies solving A from what I just showed. But solving A implies solving X. Why? Why is that true? What did I say about A? A is a known NP-complete problem. So solving A means I solved everything in NP. In particular, I solved X. Therefore, but X was any problem in NP. I said nothing about X. Other than it's in NP. I have now solved every problem in NP. Efficiently.
And then you retire.
Yes. Exactly. Yes.
So we have kind of examples of NP-complete problems, but
Not yet. I have not given you any example yet.
No, I mean in general, not specifically.
Sure, but I've not told you even one NP-hard problem yet. So okay.
But I mean, we don't know any problem to be NP-hard. We don't have any sample of that. Do we have any sample?
So yes, in the outside world we do.
Yeah, but we couldn't solve.
Well, we don't know. Yeah. But you're getting at a point I think has been raised before and is a point of great confusion. To prove a problem NP-hard requires an NP-hard problem. It's like the old joke about opening a can of beer. If you want to open a bottle of beer, use another bottle of beer. The response is, what if you have only one bottle of beer? The answer is, what do you mean? Unfortunately here, we don't have that luxury. We have one problem. To show one problem is NP-hard, we need another problem is NP-hard. To show that one is NP-hard, we need another one is NP-hard. Somewhere this path is going to stop. And then we're in trouble. So we need the Ur problem, the problem that can be shown NP-hard without doing this trick. And I guess the question is, how on earth can you prove problem NP-hard without having another NP-hard problem? Let's think about that for 2 minutes. Take a break.
Since A is NP-complete, that means because it's NP-complete, that means it will solve A. Does it mean that
says that it will any problem in NP set. So what is the way to solve it?
There are these problems that we solve and these problems that we don't know.
So why does conjunctive
So A is a problem that we can't verify. We can't solve it. If we can solve A that means
we don't know how to solve it. This is a block that we're solving, but if we can show that solving this problem also and by extension. But you say no, we can't solve it. So does it mean yes or no? It means solve it. It's really hard to show that you can solve it. It's hard to come up with those
All right, let's continue. So we left off with this question of how do you prove that the first problem was NP complete or was NP hard, which is the hard part of this whole game. And if we had no other NP hard problem to hang our hat on, it was not clear how you go about doing this. Well, that's why this was a very important result when it was first shown. Again, about 40 odd years ago. That in fact there is a problem that is NP hard, and I can show it without having to take the course to any other problem. This is the first one. And let me first introduce the problem to you, and then I won't give you the proof, but I'll give you a hint of how it came into proving. So the problem is called circuit set. And I should mention that in complexity theory, it turns out to be convenient to think of problems as questions with a yes or no answer. This gets a little bit annoying when you think of things like, well, I want to sort. But there's a way to take any problem, mostly, and convert it into some kind of decision problem where the answer is either yes or no. We will consider problems of that kind. So if you want to say, find the shortest path traveling through a bunch of vertices, we're not going to say find the shortest path. We're going to say, is there a path of length less than 5? Because that's a question in which you can give a yes or no answer. And so it's not hard to take a problem and convert it to this form. It's just more convenient for the reason that we're going to be using, to have only yes or no problems. So the circuit set is going to be a problem that has a yes or no answer, and is defined as the following problem. I give you a circuit. A circuit, of course, consists of AND gates, OR gates, and NOT gates. Right? So I have some circuit here. So maybe I have some inputs here. This goes up there, and then maybe there's an OR gate here. This goes out here. And there goes some other AND gate here. And maybe there's a NOT gate after that. And then maybe this actually came out here. And then there's another input that came here. Come out here. And I'm just making stuff up as I go. Okay. So there's one input, two inputs. Fine. And right here is a bulb. Now, of course, think of the x1 through x5 as switches that can be either on or off. You all know the rules of logic. You know what happens if you go things through an AND gate or an OR gate or NOT gate. And the question that circuit set asks is, given such a circuit, okay, Okay? So this question has a yes or no answer. Either there is a setting or there isn't. So it's within our framework of what we think about as reasonable problems to think about. And there's an input and you go to check. It's a well-defined problem. And so, in general approach, you'll have n inputs. So obviously, the solution of flipping all the switches will take too long. So there's no obvious, easy polynomial time solution to this problem. There may be one, but there's no obvious one. Conversely, though, if I gave you a set of values x1 through xn, hopefully you can convince yourself that it's very quick, easy to check if the bulb in fact does that. So if someone claims, here's my setting of switches, you just propagate them to the network. Again, the input is, of course, of size, whatever the network size is. So it'll take you time, linear or whatever the size of the network, to actually check the bulb lines up. So this problem is an NP, because you can check a given answer very efficiently in linear time problem, if you have the right answer. But the question is, can you actually find such a thing? This problem was the first problem shown to be NP in 1970. So independently by Steve Cook and Leonard Lemon. And there's nothing particularly special about this problem, which happened to be the first one. But they had to prove this without using the trick we described in the previous one. They couldn't rely on some other NP method. So how would you even think about trying to prove it? And I'm not going to give the proof here, but here's the idea. We need to show that if you can solve this, you can solve any problem in NP. Okay. What is the one thing that every problem in NP has in common? Sorry?
It's hard.
They're easy to verify. They're not hard, they're easy to verify. The definition of NP is a statement about how easy it is to do something, not about how hard it is to do something. They're easy to verify. Well, they're easy to verify means that if you gave me an answer, I can check the answer efficiently. That means that if you gave me an answer, there is an algorithm or a program that runs in polynomial time that checks the answer. So any problem in NP comes with that algorithm for checking. So when someone's here's my NP problem, it comes with the algorithm. And so the idea is you take that algorithm and you convert that into a circuit. Hopefully you all know how to convert algorithms to circuits. Every time you write a piece of code and compile it, that's what you're doing essentially at some level. So it's fairly easy to take a piece of code and convert this into a circuit. You can make sure the circuit is not very big. Okay. And then the running of the algorithm involves checking whether there's an answer that's positive or not. Again, this takes a lot of work, we have to be very careful. The fact that the algorithm runs in polynomial time means that there's polynomially many steps in it, which means that this size of circuit is not too big, it's also polynomial time, polynomial size, so everything works out. And it's a lot of laborious sort of case analysis to do this. But that's all you have to do. Because every problem in NP is guaranteed a verifier algorithm. You take that algorithm, take it into a circuit, and now if you can check that the circuit fires, you're actually checking if a verifier exists. If a verification witness exists, you have now checked if the problem. Yes?
Can we do something like if we find all the possible answers?
How long will that take? That would take exponential time.
Yeah.
You're not allowed to spend exponential time to verify. You're only allowed to spend polynomial time. Right? So that's why we're saying that if this problem was solvable in polynomial time, then we have a solution for any problem in NP in polynomial time. Because we took that verifier for that problem, converted to a circuit, then we're asking, is there any way to make that verifier say yes? That's exactly what we want for that problem. Finding a witness that says the verifier says yes. So again, there are places where you can actually look at the Gordy to prove a number. But that was the first problem. That was sort of kicked off this whole area in some sense. And once we have this, we can hook up many things.
Was that the key idea, how the solvers were actually designed, the SAT solvers?
In some sense, yes.
Because they actually verify, like, for example, for a given expression, if you have to say whether that is satisfiable or unsatisfiable. So it will work out on all the given inputs, and then it can, come up with the result, whether sat or unsat.
Right, but it's not looking at all the possible inputs. The SAT solvers are much cleverer.
Yeah. So, I mean, if you
But the idea of the reduction to SAT, yes, it's sort of connected here. You're taking an arbitrary problem and reducing it to circuit SAT. So yes, that is correct. Other questions? Discussions? Yes?
In some sense, P problem can also be reduced to a circuit.
Oh yes, absolutely. That doesn't contradict anything.
Then I didn't prove anything.
Why?
If I can solve a P problem to circuit and solve it, and then an NP problem also to.
Yes, but what is my goal in showing a problem is NP hard? That every problem in NP can be solved if I can solve this problem. I don't care about the problem. They can be solved anyway. What do I care about?
But there are particular circuits that I can solve, right?
Yes. But what I'm saying is not that. I'm saying take an arbitrary problem in NP. I will show you how to solve this arbitrary problem using a solution for circuit SAT. And the only way I have, the fact that I can do this is because any arbitrary problem in NP must come with a verifier. Otherwise it's not NP.
Since you have verified, you can write it as a circuit.
Yes. You can write the verifier as a circuit.
Verifier.
Then the question of does there exist a witness becomes does there exist a witness here? Let it sit for a bit. These things make it there is a slightly different version of this problem that we find to be convenient. It's called SAT instead of circuit SAT. So the problem of SAT, instead of given a circuit, you're given a Boolean expression. So you're given maybe, you have x1 or x2 or x3 bar and x1 bar or x5 and so on and so forth. Okay. Same question. Is this satisfiable? Can I set this? Can I set the variable so this whole expression becomes 1? It's not hard to see that these are two basically the same problem. We just rewrite the expression in this form. This is called, by the way, a particular form of SAT. This is called the conjunctive normal form, where basically all the ors are inside and all the ands are outside. Which means you have to satisfy every clause, but with each clause you have some choices about how you satisfy it. Any one of these need to be. There's a different form called disjunctive normal form, which is the reverse, which is not an NP problem. Because you just need to satisfy one of those things. If it's an and everything is or, you just pick one and it's satisfied and you're done. That problem is not NPR. This problem is. Okay. So I will prove this, but we're gonna. What I'm gonna do is explain to you now how you show that a particular problem is NPR. Okay, for any given problem.
Can you not take a SAT problem and change it to, like, change all the ands to ors by conversion?
Yes, you can. Your formula becomes very big. What happens if you take all and you do use De Morgan's laws and you multiply out all the ands and ors, your formula goes to an exponential size.
Okay.
And we'll see in a second why it's not allowed. Intuitively, you should see why that's not allowed. Okay. So let me define to you what a reduction is. So we're going to say that we had this statement 2 slides ago, I think, that said something like this. Find an NP can be problem A. If I can solve P, I can solve A, and then we're done. I want to explain this now in a bit more detail as to how you go about showing that the problem is hard to solve. Okay. And this brings us to the topic of reductions. Okay. You've all seen reductions, you use them all the time. Every time you call a subroutine, you're basically using reduction. You're saying use B to solve A. So let me define to you in a more formal way what a reduction is. So a reduction involves 2 problems, A and B. And I want to A to B. Remember, these are decision problems. So what I'm going to say is that I have some input. So A is a problem class, right? A is the problem of, finding a traveling salesman tour in a graph. So that every problem has a notion of an input. The input to the problem, and you want to check something on it. So let's say you have some input problem, X, and it belongs to, and we want to know if it belongs to A or not. Right? This is the class of things where you can actually solve this problem. Okay? A reduction basically is a couple of things. It involves, number one, a function that maps instances of A, so we'll call them instances of A, to instances of B. Okay? So namely, given an X input, that might or may not be an A, you construct an f of X, which may or may not be a B. Okay? So and then the next step is going to show that X is an A if and only if f of X is a B. So what I mean by this is that, remember that I said my problems either have a yes or no answer, right? So if you think of, again, problem of satisfiable circuit set, you can think of circuits that have a way to make the light fire and circuits that don't have a way to make, that there's no way to make the light fire. The yes instances and the no instances. Okay? We'll say A is a set of all yes instances of a problem. So when we have an input X, we're saying if X is an A, we're saying that there is a way to make the bulb fire. If X is not an A, we're saying there's no way to make the bulb fire. A reduction says, rather than trying to figure out if the bulb can fire or not, we convert X to some other problem, we're going to ask the same thing. Does that problem have a solution that's yes or no? And again, this all makes more sense once I give you an example. So let me just, without further ado, let me give you an actual example. So let's see. So let me just finish this thought here. Once I reduce A to B, now we know that if A was NP hard, then so is B. I should have mentioned this reduction has to work in point. Alright. Now again, instead of dwelling on this more abstract thing which is clearly causing some confusion, let me just give you an example. Okay. Let me just go to a new page while you try to do this. Okay, so we have the problem of circuit set. And we know circuit set is NP complete. Because I told you. And now we have the problem set, which is basically a bunch of formula, and you want to check if the formula is satisfiable. And we want to know, is it NP complete? How would we go about showing this? So first of all, number one, I claim that SAT is an NP. And this should be relatively easy to see. I claim that if I give you a solution, a set of variables true and false for a formula, I can check if that formula is true or not. Do you believe that? That if I actually tell you, okay, x1 is true, x2 is false, and I can evaluate the Boolean expression and check if it's true or false in Polymer time, actually linear time. Okay. So just evaluate the formula. So okay. The second thing we have to show now, to show it's NP complete, is that SAT is NP hard. And to do that, we are going to reduce circuit SAT. And I'm going to stop here and say something that I say every year in this class, and it still remains true. Every one of you is going to make a mistake and do this reduction the wrong way around. At least once. Just make sure you don't do it more than once. If you want to show that a problem is hard, you have to take some other problem and reduce that to this, the one that you're trying to show hard. Not the other way around. And trust me, it'll be very tempting to do the other way around, because you have the unknown thing, you want to make it look like something you know. That's not how reductions work. That's not how the implication works. You have to do it backwards. Okay? So in order to show that SAT is NP hard, we take some problem that's known to be NP hard and reduce it to our unknown hardness problem like SAT. Okay? In order to do that, we need to look at what these two problems represent and construct a mapping from one to the other. Okay. What is the input? So what is the input to a circuit SAT instance? What is a circuit SAT instance input? Yes,
Could you just say one more thing about intuition? Because exactly, I was going to
do we go the other way around?
I was going to go the other way around.
Good, very good. It's a very natural way to think. The intuition is this. If you want to We want to say that this problem is very hard to solve. That's what we want to show. So we have to do the reduction this way, because what we're going to say is this. I know this problem is hard to solve. You just told me I can solve this problem using this. The only way there is no further contradiction is if this problem is also hard to solve. Right? Because you're doing it backwards. That makes sense? It's very important, and it will be easy to get this confused. We're trying to show that something is hard to solve. So we need to show that if in fact it were easy to solve, some other problem would become easy that we know is already hard, which is a contradiction. Therefore, it must be hard. Okay? Alright. So now we want to reduce circuit sat to sat. So the first question we have to ask ourselves is, what does an input to circuit sat look like? What is an input to a circuit sat problem? Sorry? Hearing voices, sounds? A bit array. The input to circuit sat is not a bit array, it's a gate, set of gates.
Oh yeah.
The input to circuit sat is a gate sequence. And the question we're asking is there a way to get this gate sequence set to 1 at the end? Right? So the input is not the bit array, that's the output. The input is the set of gates. Okay, so the input to circuit sat is right here. So the circuit sat instance is a sequence of is a circuit of gates. Right? What is the input to an instance of sat? The problem I just mentioned. It's a formula. Right? With ands and ors and nots in it. It's a formula. So a sat instance is a formula. A Boolean formula. Okay? The first step in our reduction, again, think of this as if you're writing code. I want to write code to solve circuit sat. I have a subroutine that solves sat. So what do I need to do? I need to take my input and get into a form that I can plug into the subroutine, right? How do I take that input, a set of gates wired together, and convert it into a formula that I can plug into my sat subroutine? What do I do? So let's take a simple example. Let's say I have just one, my input to circuit sat consists of just one gate. Okay? What is the corresponding formula for this? Sorry? Right? What is the, similarly there's one for OR. Right? And so, and there's one for NOT. So now if I have some complicated circuit, so maybe it starts off, right? So what might I say? Well, this will be a formula that looks something like right? Given any instance of a set of gates wired together, which is an input to circuit sat, I can rewrite it as a formula. Yes?
Do you have to be able to rewrite it efficiently?
You do, because the function has to run. And why is that important to do it efficiently? That's a very good question. Why is it important to do this efficiently?
Because even if the problem is easy to solve, you can't, if it takes forever to get it into that form.
What's the point? You haven't proved anything. Exactly. Very good. So it is important this reduction be done efficiently, because I'm saying that I can solve this hard problem using that easy problem. Right? The contradiction only occurs if this whole process is in fact easy. Because then I have easy problem, easy reduction, easy solution here, but this was hard. If I have to climb through mountains and cut through forests to get there, it's not going to help. So it is very important this reduction be easy. So good. How long does this reduction take? If I have an input consisting of n gates, right? How long do you think it's going to take to write down this expression?
And
You just linearly you just write them down. You go work backwards from the end. Maybe it takes n squared. Maybe you're not being careful with your structures. As long as it takes polynomial time, you're okay. That's all we care about. But you should take only polynomial time. And you can imagine this working recursively backwards like this. You should really do this. So step 1 of the reduction is construct efficient mapping. And we've just done that. Step 2 is to show that there's an if and only if condition on the yes answers on both cases. In other words, circuit sat instance has a 1 answer if and only if sat instance is satisfiable. That's an if and only if. So how do we prove this? What we want to say is that if the instance, the circuit sat instance actually had a way to make the bulb go off, then there's a way to make this formula satisfiable. Is that clear we can do that? How do we make that argument? How do we prove that if there's a way to make the bulb go off for the gates, then in fact this formula is satisfiable? They're kind of equivalent.
Yeah, I mean, that's, I don't know how you would say it mathematically, but.
Right, they're kind of equivalent. And they're kind of equivalent because what we can say is the following, right? Again, let's go back to a single gate. We can say something like this, right? x1, x2. The way to fire this is set to 1 is to set x1 equal, x2 equal to 1, right? The way to set this corresponding formula equal to 1 is also to set x1, x2 equal to 1. So the proof is basically that if the CSAT instance has a bulb going off, right? Then take the values you used in the circuit sat instance to set the bulb to 1 and use the same values in your sat form. So they're equivalent, but they're equivalent because you just take the same value and copy it over. In general, this will not be that simple, but you can do it this way. Conversely, and that's one side of the if and only if your sat formula is satisfiable, what are you going to do? How do you show that the circuit sat instance will set the bulb off? Take the values and feed them back to the circuit. By the way we did the construction F, we know that these things are equivalent. Right? An AND gate fires if that particular formula is satisfied. And you can write this down just precisely saying, okay, this is equivalent. The truth value of a gate is the same as the truth value of the formula. And so you get the if and only if, and you are done. Having proved these 2 or 3 steps, if you think of this as 2 parts in itself, you have now shown that circuit sat reduces to sat. We know by fiat that circuit sat is NP hard and complete in fact. Therefore, sat is NP. And now we have 2 terms. So, yes.
So what is efficient mapping? How efficient should be?
Follow me next. That's all you need.
So when you're saying CSAT is NP hard, are you saying some CSATs are NP hard or all CSATs are NP hard?
NP hardness is a function of the problem. NP completeness is a function of the problem, not an instance of the problem. An instance of the problem is either true or false.
Yeah.
It's the NP hardness refers to the class of problems.
So my question is, if algorithm 1 is not NP hard.
No, wait. There's a type mismatch here. An algorithm is not NP hard. A problem is NP hard.
Okay, yeah.
Circuit sat is a problem. There may be algorithms to solve that problem, but it's a problem.
Okay.
We're reasoning about problems here and about classes of problems. Okay? We're not reasoning about We're actually, but of course we are constructing a particular algorithm to convert an instance of one problem to an instance of another problem. That's what our reduction is doing. So ultimately we are designing algorithms. But yeah. We're going to do some more practicing on this. But the other subtle point that I want to bring out here is that you have to construct this mapping for the instance without knowing whether the instance is true or not. The mapping has to work regardless of whether there was a way of getting the bulb to go off or not. You can't assume that, okay, let's assume that this is an instance where the bulb does go off and I'll do something. You can't do that. The mapping has to work agnostically, because if you think of this as writing code, I'm going to take any input to that problem and then convert it to an input to this problem and then see what the answer is. I don't know what the answer is going to be ahead of time. That's the whole point of the reduction. So often you will come up with a reduction where you'll say, oh wait, let's assume that in fact my graph had a traveling salesman tour of cycle. You can't do that. It has to work regardless. That's what makes these things very hard. They have to work regardless of what the input actually has in it. And you have to go kind of backwards from the known problem to the unknown problem. And this is basically, this two-step process is how every problem is shown to be in the many thousand problems we now learn were all shown this way. Take some known NP problem, reduce it to your unknown problem. So sometimes you have these chains of reduction. And if you look at a paper, it'll have, okay, we want to show this problem is NP complete. We first went, this is auxiliary problem 1, auxiliary problem 2, auxiliary problem 3. That, now there's a known problem, it goes to, next shows auxiliary problem 1 is NP hard, which then is used to show auxiliary problem 2 is NP hard, don't do any further. So some of them can be quite interesting. We won't be studying those in the class, but we can get pretty involved. So this is a lot to digest, I think, and I think we should, it's kind of good, it's a Thursday, get a time sort of distill those. We'll continue this again next lecture, but I'm not done yet. So, but this is not something that you should expect to understand in a minute. It takes a while to absorb. Okay? But in the next 10 minutes or so, what I want to make sure is that you at least understand right now the mechanics of what we're doing and why. This step process. So just run this through in your head right now, what we're doing. Let's see if you understand those terms. Yes?
So, in terms of what you proved is, given an NP hard problem, how we proved how other NP hard problems can be related to this problem.
Well, we've proven how to make sure that the new problems are NP.
Yes, given a problem that we had. But but the first problem to prove one problem that we had is still there, right?
That's circuit set. But that I told you I gave this outline of how they did it.
Yeah,
they took an arbitrary problem and had a verifier and they converted it.
But if you have two problems, one is NP hard and one is not, both of them can be written in C side, right?
You've just made the mistake I said you shouldn't make. That's good. I told you I was going to make 3 videos. You're not going to make any more though. You're not going to write that problem as C circuit set. You're going to take circuit set and write it as your problem. Yes, I know. I had the same feeling when I first listened. Yes.
So is the way to think about this maybe that you're trying to find a bound for your problem, and so you want to reduce the hard problem to your problem to get that bound, right?
Yes. That's correct. Because you're trying to find a lower bound for your problem. See, normally you're trying to show that problems are easy. So you want to take our problem, which is hard, and reduce it to, and then say that, we can solve our hard problem into an easy problem and we're happy. We try to do this the other way around. That's why you have to go from the problem that's known to be hard to our problem. Right. Because you're going to control positive. Questions?
Can you go to the page of P&A statement?
Yes.
Yeah, so why do you define A as a NP complete problem, not NP or P problem?
What I want to do is show that P, my problem, which is a bad name because P is a class as well, but my problem is hard. That's what my goal is. Okay? I want to show my problem is hard, so I want to show that solving my problem solves a well-known hard problem, A. Right? If solving my problem would solve a well-known hard problem easily, then something is wrong somewhere. And so the problem has to be my assumption that my problem was solvable. Therefore, my problem must be hard. That make sense?
So do you mean that you can anyway find a NP complete problem A?
I can take any NP complete problem A, yes. And show that solving my problem would solve it.
What if when you can solve your problem, but you cannot solve it?
Then you have not constructed a reduction. Then you cannot, if you can solve your problem and you cannot solve A, then you solve your problem. So it's good in one way. But you have not established the problem is hard anymore. That you have to have the hope that solving mine will solve this hard problem in order to make me also hard. So you think of the easy problems, the hard problems. Yeah, this hard problem kind of pulling your problem into that class. And so the actual mechanical process by which we say, if I can solve P, I can solve A, is what I call a reduction, which has those two steps to it. So when you say, okay, how do I do this? You do it by a reduction, and the reduction has these steps. Okay. You had a question?
How do we know circuit stat is hard?
Because I declared it by fiat. So in other words, I did not prove this in class.
Is there a proof for it?
There is. That was the famous paper that was shown in 71. The notes sort of sketch out how it was. It's one of these very tedious long proofs. The idea was that you take an actual algorithm for doing verification of an arbitrary problem, and you convert every if-then clause into a formula. You know, you take an if-then-else statement, you make it go to a bunch of gates. You take a loop, you convert to a bunch of gates. You take everything else, you convert to a bunch of gates. It's a gigantic gate sequence, but it's only polynomial sized. So the reduction works efficiently, and then you say that whether a verification witness exists for this problem is the same as saying that I can put the bulb on. So I construct exactly this reduction, but for that problem. But because it's an arbitrary NP problem, you have to reason abstractly about the existence of a verifier. It's much less tangible. But that's exactly it. Yeah. Yeah. Yes?
You can say if there are n inputs, because it's Boolean, there are 2 to the n possibilities.
Yes.
It's exponential. So it's not polynomial.
No. Well, what is not polynomial?
The input possibility.
Yeah.
The number of possibilities is not polynomial. That doesn't mean it'll take that long to find the answer.
But it could.
Well,
Sure, it might, it might not.
Check everyone.
See, but that's not normal. That's saying it takes no more than exponential time. You just give me an algorithm that runs an exponential time. That's great. But that doesn't mean it has to take exponential time. Right?
Yeah.
You don't seem convinced.
Well, I'm just trying to say that this is not a polynomial type of problem.
What is not a polynomial problem?
Circuit stat.
How do I know?
You can
Just because, just because there are 2 to the n possible ways of setting the inputs doesn't mean I have to explore all of them. Let me give you another problem, which has an exponential, even worse than 2 to the n possible ways of setting inputs. I have a bipolar graph, and I have nodes on one side and nodes on the other side, and they have edges between them, and there are weights. And I want to figure out a way to match nodes here to nodes here, so the sum of the weights in these things, in these correspondences, is maximized. There are n factorial ways to do this, but I can solve this in polynomial time. It's a maximum matching problem. Just because there are exponentially many ways you could imagine this happening does not mean you have to search through the entire space. So don't confuse what could happen versus what needs to happen. This is the hardness here. You may be right eventually. You don't know. It may be that in fact you have to take that much time, or you may be wrong. I can't say you're wrong, but you can't say you're right. That's the situation we're in right now. That's all we know. So, but be careful not to fall into that trap. That's a very common trap to fall into. That okay, I have so many inputs, there's no way out. There might be. And think about matchings. Let me think about it. Yes.
So, I have kind of a confusion about the deduction.
Sure.
So we say that if I can solve my problem, it results to solving a hard problem.
Yes.
Why couldn't we say that solving my problem requires solving a hard problem? So I cannot solve this one.
How would you say that it requires? That's a much harder statement to make. You're saying that of all the amazing, brilliant ways I could think about solving problems, they all require the other problem. That's really hard. If you can do that, more power to you. But I don't know how to prove such a statement. That's a very hard statement you're asking me to prove. So yes, you might be able to do it, but that's really, really tough. You're saying every path goes through that block right there. I'm trying to prove the same thing you want in the easier way. But your statement would also prove what you want to prove, which is it's a lot more difficult. Yes.
So, what we all just said, this applies to all levels of these machines, right? Or
All levels of?
Of just models of computation.
Yes. In fact, but you have to be more careful. For example, if you want to talk about, for example, are all sequential algorithms parallelizable? It's a question that people look at. There's a complexity class which is P, and there's a complexity class called NC, don't worry about what it means, which is the class of all things that can be efficiently parallelized. You can do the same thing there. You can say find reductions and find hard problems. There's problems called a P hard instead of N hard. You can do the same thing. But the reduction, the F function, has to have a different complexity now. It doesn't make sense now to talk about polynomial time complexity. You have to talk about a lower complexity. So if you're talking about reductions among classes that are simpler, the reduction itself must be simpler. If you're talking about classes that are much bigger, then your reduction itself could be a lot more complicated. So it depends. So since we're talking about polynomial time versus what might not be polynomial or whatever, it's okay to have a polynomial time reduction. But if you're going down below the log space and other kinds of classes like that, you have to change the definition of reduction. So that the way you construct the F depends, or the efficiency are allowed to use in constructing F, depends on the classes you're trying to work with. But the mechanics of reduction are exactly the same. You construct the function and you just look at the efficiency. That make sense? Good question. Okay. I will see you all next week. Have a horrifying Halloween.
Since they can solve it, I can't say can solve it. But if they